Imagine two wristwatches, born identical on the same workbench. One stays behind, ticking in the quiet of a city square. The other is carried aloft, first by jet, then by rocket, until it circles Earth aboard the International Space Station. Months later, the traveling watch returns, and the two dials disagree. The difference is tiny, mere microseconds, yet its message is immense. Time is not a universal drumbeat. It stretches, it compresses. It can be persuaded to flow at different rates along different paths. Across the last century, this humbling fact has crept from chalkboards into daily life. Your phone's map relies on satellites whose onboard clocks tick faster in orbit than ours do on the ground. Engineers must deliberately slow them so that directions stay true. Mountaintop laboratories measure gravity's pull not with weights and pulleys but with clocks, noting how seconds lengthen as altitude rises. Everywhere we look, the universe whispers the same secret. Motion and gravity are not just about where you go, they reshape when you are. Tonight, we ask the daring question that has haunted storytellers and scientists alike. If time can flex, could it ever fold? Could a clever civilization, or the universe itself, tie moments into loops, letting effect precede cause, or yesterday meet tomorrow face to face? To explore that possibility, we will walk a tightrope between hard experiment and bold speculation. We will meet spinning black holes whose interiors may, on paper at least, curve back on themselves. We will weigh the strange fuel, negative energy, that theory demands, but nature grudgingly rations by the thimbleful. Quantum fields will join the discussion, hinting that entanglement might offer shortcuts no rocket can match, while at the same time erecting subtle safeguards against temporal mischief. Yet this journey is not a chase for fantasy machines alone. Every step will illuminate the physics that already governs our lives. Why aging astronauts return fractionally younger? Why the core of the sun glows thanks to quantum tunneling across time as well as space? And why the arrow of causality? So familiar we rarely question it may be as fragile as a snowflake in the furnace of cosmic possibility. We will move gently, with clarity, pausing whenever ideas grow strange to translate them into the language of everyday experience. And we will proceed with humility, mindful that nature often keeps her deepest answers just beyond the next horizon. So keep one eye on the watch upon your wrist, and another on the night sky overhead. Between those two ticking faces lies a cosmos where seconds can bend, paths can diverge, and perhaps, just perhaps, the river of time may swirl back upon itself. The first clue came not from science fiction, but from a simple thought about twins in a very fast train. Picture a sleek midnight express racing across a prairie. Rain clouds brood overhead. Two lightning bolts strike the track, one at the engine, one at the caboose, so close in time that to a station master on the platform, the flashes seem perfectly simultaneous. But inside the train, a passenger sits midway between carriages, eyes wide as both flashes burst in her windows. She swears the strike at the engine comes first. After all, the train is rushing toward that flash and away from the other. Who is right? Albert Einstein, in 1905, answered with quiet audacity. Both are. The speed of light, he declared, is the same for every observer, no matter how fast they travel, because that speed cannot budge. What can adjust is time itself. The train passenger and the station master inhabit different slices of space-time, each with its own ordering of events, neither privileged, both valid. From this single insight flows the phenomenon we call time dilation. If simultaneity is relative, so too is the tick-tock that measures it. A moving clock must run slow compared with one at rest, otherwise the equations of motion and light's fixed pace would clash. The faster you dash through space, the thinner each second stretches. You needn't trust theory alone. Muons born in Earth's upper atmosphere live barely 2 microseconds before decaying. Yet because they race downward at near-light speed, their internal clocks lag. They endure long enough to reach detectors on mountain slopes, a natural proof written in cosmic rays. Motion and light's steadfast speed conspire to bend the rhythm of time, making simultaneity and eventually aging itself a matter of perspective. Now imagine twins, Lena and Myra. Lena boards a starship capable of half the speed of light. Myra stays home, tending a garden that will bloom many seasons before her sister returns. During the outbound leg, Lena feels weightless serenity, her engine silent. At midpoint, she fires retros, flips, and races back. When she steps onto Earth once more, she discovers the garden has grown wild. Mira is years older, while Lena has aged only months. Where did the extra time go? At first glance, the scenario seems symmetric. Each twin sees the other moving. The key difference hides in the turnaround. To pivot homeward, Lena must accelerate, switching from one inertial frame to another. That brief burst breaks the symmetry, carving a kink in her path through space-time. Think of time like budgeted fuel. Every traveler owns the same allowance of space-time ticks. But how you split that allowance between motion through space and motion through time is up to your journey. Lena spends lavishly on speed. Mira spends none. Physics reimburses the frugal twin with more aging, fast twin with less. The paradox is no longer a puzzle once we track proper time, the accumulation of seconds along each traveler's personal route. Calculated carefully, Lena's path simply contains fewer seconds than Mira's. No clocks were damaged. The universe kept exact books. Real-world echoes abound. In 1971, atomic clocks flown around the globe returned nanoseconds younger than their ground station siblings. Today, astronauts aboard the International Space Station amass roughly 0.02 seconds of youth each 6-month tour. Velocity carves shorter corridors through space-time. Choose a swift route, and time itself grants you a modest rebate. Proof that forward time travel is already woven into everyday physics. In October 1971, 3 men arrived at Washington Dulles carrying luggage that ticked. Inside were 4 suitcase-sized cesium clocks, so precise they would lose barely a second over a million years. The scientists bought airline tickets, split into eastbound and westbound teams, spent 2 days chasing the sun across the sky. When the clocks reunited in a basement lab, they no longer agreed. Those that had raced with Earth's rotation were slow by 59 nanoseconds. The westbound set, flying against the spin, it gained 273. The differences were tiny yet matched Einstein's predictions to the nanosecond. Commercial jets had turned cabins of coffee and carry-ons into moving laboratories, proving that velocity can bend time as surely as wind bends grass. Today, that experiment plays out continuously overhead. Each GPS satellite carries atomic clocks that tick 38 microseconds faster every day than clocks on the ground. Partly because they speed through space, partly because they hover high above Earth's pole. Engineers dial the satellite clocks back before launch so that, once aloft, they drift forward into perfect sync. Without that relativistic correction, your phone's blue dot location would wander kilometers every hour, sending commuters into rivers and aircraft onto empty runways. On mountaintops, research stations host similar tests. Two optical clocks, one near sea level, one high in the Andes, are compared by laser. The loftier clock consistently races ahead, revealing that a change of just 1 vertical meter adds roughly 1 part in 10 to the power 16 to the tempo of time. Resolution fine enough to sense the slow flex of continental plates. Whether flying at 900 kilometers an hour or orbiting at 14 times that speed, moving higher and faster lets you sample tomorrow a heartbeat early. Time dilation you can navigate by and even build a civilization upon. Stand at the base of a skyscraper and aim a beam of light toward the roof. To the photons, that short climb is work against Earth's gravity, and they pay the toll by lengthening their wavelength. An effect called gravitational redshift. In 1960, 2 physicists, Robert Pound and Glenn Rebka, shrank that cosmic drama to a 22-meter tower at Harvard. They aimed gamma-ray photons downward and upward and measured a frequency change of just 1 part in 100 trillion, exactly as general relativity foretold. The reason is simple yet profound. Gravity dilates time. Deep in a planet's well, seconds stretch. Climb higher, and the cosmic metronome ticks a shade faster. High-altitude bakers may need to adjust recipes because water boils cooler. But far subtler tasks depend on gravity's slow tick. Financial institutions synchronize transactions to billionths of a second. Geologists map subterranean cavities by noting which path makes a portable clock run slower. Even your own body experiences this gradient. Your head is centimeters higher than your heart, aging a teeny-weeny bit faster each night. Over an entire lifetime, the tally reaches a few nanoseconds. Trivial to biology, vital to physics. It means that every human, by simply standing upright, inhabits a personal timescape ever so slightly stretched from toe to crown. Black holes turn this gentle slope into a cliff. Approach the event horizon, and external observers see your clock slow to a crawl, frozen in a farewell wave. Time itself becomes a fragile local privilege, a property set not by calendars but by curvature. Gravity is more than a downward pull. It is a sculptor of seconds, slowing the beat of time wherever mass gathers and reminding us that even standing still will live on a tilted clock face. Every evening aboard the International Space Station, astronauts float into their sleeping pods, having leaped a little farther into tomorrow than we have. After 6 months in orbit, their clocks read about 0.02 of a second ahead of ours. It is a sliver, but it is real, earned by 90-minute 28,000 km/h laps around Earth. Down on the ground, muons born in cosmic ray collisions set the ultimate record. At rest, they should vanish in microseconds. Yet in particle accelerator rings, racing near light speed, they linger 10 times longer. Velocity distends their lifetimes, handing them a brief taste of the future before they fade to nothing. Even everyday devices join the tally. Each time your phone checks in with GPS satellites, it relies on clocks that have already aged millennia ahead in orbital microsteps. Modern life navigation, banking, even dating apps functions only because engineers correct for those multi-second leaps across the constellation. So far, every confirmed voyage is one way: forward. Relativity lets us stretch the timeline, never fold it. But nature's equations hold stranger solutions. Regions where gravity spins space into loops, where negative energy might tunnel causal walls, where quantum entanglement whispers of shortcuts no rocket can fly. In the chapters ahead, we will tiptoe toward those frontiers, asking how far speculation can lean on mathematics before the fabric snaps or reveals an unexpected seam. We already travel through time, just forward, and never equally. So the next question is whether space-time might allow a return ticket.